Module 2, Lecture B, Text and Files. By the end of this lecture, you will be able to manipulate medical text strings to clean labels, notes, and simple patient instructions. Read and write plain text or CSV-style medical data using built-in file handling. Use standard library modules to support safe paths, dates, and simple structured output. Clinical text cleaning. Cleaning clinical labels. Cleaning clinical labels means standardizing medical text so it stays accurate but becomes easier to read, sort, and analyze. Labels often differ because different people write the same idea in different ways, such as varying capitalization, spacing, or abbreviations. Basic text cleaning reduces these inconsistencies, making the labels more predictable and useful for both humans and computers. Standardize clinical labels by removing extra spaces, making internal spacing consistent, and using consistent capitalization. Also normalize separators so similar labels can be compared accurately. However, preserve clinically important details because punctuation and capitalization can change meaning, such as the difference between milligrams and micrograms. The goal is consistent formatting without losing critical clinical information. When cleaning clinical labels, preserve meaning while improving clarity. Consider abbreviations, local naming conventions, and who will use the labels, since analysts may need compact terms, while patients need clear and respectful language. Avoid oversimplifying, because important distinctions, such as left versus right, can be lost. The goal is cleaner, more usable data without removing essential clinical detail. Python code. Cleaning clinical labels. Clinical labels are often inconsistent or messy, so simple string cleaning can help reduce unwanted variation. The key is to standardize the text without changing its clinical meaning. The script imports the regular expressions module to help clean clinical labels. It uses pattern matching to remove unwanted characters and fix formatting inconsistencies, making the labels more standardized. This approach is efficient and flexible for handling messy, raw clinical text. We start with a list of clinical labels that are short, messy text strings, similar to what might appear in real clinical data. The labels include inconsistent spacing, underscores, prefixes, and periods. This variety helps demonstrate how common formatting problems can be cleaned and standardized. This label cleaning function standardizes clinical labels while keeping their meaning. It trims extra space, replaces underscores, dashes, and periods with spaces, collapses repeated spaces, and removes the unnecessary vitals prefix. It then converts the label to lowercase and capitalizes the first letter, producing a clean, consistent label for use in clinical data. A list comprehension can apply the clean label function to every raw label, producing a new list of cleaned labels. This makes the transformation concise, readable, and efficient, while applying the same cleaning rules to each item. We pair each raw label with its cleaned version by combining the two lists using the zip function. This creates tuples that link the original and cleaned labels, making it easy to compare them and show how each label was transformed. The output begins with a short header that introduces examples of cleaned clinical labels. It then compares each original label with its cleaned version, making the transformation from raw text to processed text easy to see. This direct before and after view shows how well the cleaning process works. The code prints a reminder to keep clinical units distinct during data cleaning. It warns that confusing similar units, such as milligrams and micrograms, can change the meaning of a measurement and lead to serious errors. This script standardizes clinical labels while keeping their meanings accurate. It cleans formatting with regular expressions by removing extra spaces, changing underscores and hyphens into spaces, dropping prefixes such as vitals, and applying consistent capitalization. It then shows each original label beside its cleaned version. The key caution is that clinical units must not be blurred, since terms like milligrams and micrograms have different meanings. Cleaning clinical notes. Clinical notes are written mainly for people, so they often contain irregular spacing, mixed capitalization, abbreviations, and spelling errors. Text cleaning makes these notes more consistent for search and analysis by trimming spaces, standardizing capitalization, and removing formatting artifacts. The goal is to improve computer processing while preserving the original clinical meaning and voice. When cleaning clinical notes, preserve the original medical meaning above all else. Even small edits to wording, punctuation, or capitalization can affect abbreviations, medication names, dosages, or whether a symptom is present or denied. The goal is to fix surface issues like spacing or readability without changing clinically important information. Clinical notes vary by source and style, so cleaning should match the intended use. For care teams, this may mean improving spacing and line breaks. For quality checks, it may mean normalizing equivalent terms while preserving the original wording. For patient instructions, remove repetition without changing the clinical meaning. Always keep the original note with the cleaned version, so accuracy can be checked and the clinical context respected. Python code, cleaning clinical notes. Clean clinical notes with care so the original meaning is preserved. Keep the original text alongside the cleaned version to support accuracy and comparison. We begin by importing the regular expressions module called RE to support text cleaning and pattern matching. It helps search, replace, and format text efficiently, which is especially useful for processing clinical notes while preserving their meaning. The script begins with 3 sample clinical notes stored as text examples. They include common details such as symptoms, abbreviations, vital signs, medication instructions, walking distance, and wound size. These notes provide simple test cases for demonstrating the text cleaning process. The clean note function makes clinical notes easier to read while preserving important information. It replaces line breaks with spaces, standardizes long runs of hyphens, collapses extra spaces, and removes spaces from the beginning and end. The result is a cleaner, more continuous note that is better formatted for review or further processing. A new cleaned notes list is created by applying the clean note function to each clinical note. This uses a list comprehension to clean every note efficiently while leaving the original notes unchanged. The result is a matching list of cleaned versions that can be compared with the originals later. The code prints a header, then loops through each original clinical note and its cleaned version together. For each pair, it displays the note number, the original text, and the clean text, while preserving the formatting. This makes it easy to visually compare the raw and cleaned notes. The code checks that key negation words, especially denies, remain in the cleaned clinical notes. It does this by lowercasing the first cleaned note and searching for the word. This helps confirm that cleaning has not changed the note's meaning, which is especially important in clinical text where negation affects interpretation. The code checks whether the cleaning process preserved negation in a clinical note by confirming that the word denies is still present after cleaning. This matters because removing or changing negation can alter the note's meaning. It then prints a brief confirmation showing whether this critical information was preserved. This script cleans a small set of clinical notes while keeping their meaning intact. It uses regular expressions to tidy spacing and simplify repeated dashes, then compares each cleaned note with the original. It also verifies that key negation terms, such as denies, are preserved, helping ensure the notes remain accurate, readable, and clinically relevant. Cleaning clinical labels. Cleaning clinical labels helps make medical data consistent, readable, and reliable for comparison and reporting. These short labels often describe diagnoses, medications, or other key concepts, but small differences in wording or ambiguous abbreviations can cause confusion. The aim is to standardize the labels while preserving the clinical meaning and important nuances needed for accurate interpretation. Standardize clinical labels by removing meaningless variation, such as extra spaces, inconsistent capitalization, and uneven punctuation. This helps ensure that equivalent terms, like different forms of ICU or medication labels with varied units, are treated consistently in analysis. However, handle punctuation and abbreviations carefully because they may change meaning or create ambiguity depending on the medical context. Effective clinical label cleaning means making labels consistent and understandable while keeping the original terms available for review. Cleaned labels should support reliable dashboards and analysis, but they must also preserve important clinical differences between patient situations. Traceability is especially important when errors or assumptions could affect patient safety or research. Python code. Cleaning clinical labels. Clinical labels can vary in small, inconsistent ways, so built-in strings can help standardize simple medical terms. Keeping the original labels is still important, so clinical cleaning remains traceable. The script imports the regular expressions module to work with text patterns. Here it is used to clean clinical labels by managing repeated spaces, making the text more consistent and readable. This is a common use of regular expressions for searching and modifying strings. We define a list of raw clinical labels that may contain inconsistent formatting or wording. For example, one blood pressure label has extra spaces that need trimming, while another uses the abbreviation BP, suggesting the labels may also need standardization. A set of raw clinical labels is being prepared for cleaning so the terms become consistent and readable, while the originals remain available for traceability. The examples include fixing extra punctuation, standardizing units to lowercase, trimming extra spaces, and mapping informal synonyms, such as ICU ward, to a more formal label. This code creates a synonym mapping to standardize clinical labels. It links common lowercase terms or abbreviations, such as BP or ICU ward, to their full clinical names. This helps replace inconsistent labels with clear, standardized wording across the data. The function cleans a clinical label without changing its meaning. It removes extra space from the beginning and end, then reduces repeated internal spaces to a single space. This standardizes labels and helps correct spacing issues from data entry. This step uses regular expressions to clean the text by turning repeated commas into a single comma. It standardizes the label's format while leaving meaningful hyphens unchanged, helping preserve the label's intended meaning. This code standardizes unit capitalization in the text by converting forms like 500 mg into 500 milligrams. This makes medical labels clearer, more consistent, and more professional across the dataset. This line standardizes a label by checking it against a synonym map. The label is converted to lowercase, so the lookup ignores capitalization. If a known synonym is found, it returns the standard label. Otherwise, it keeps the original label. This helps make cleaned labels consistent before further processing. The code makes the label easier to read by converting it to title case, capitalizing the first letter of each word. After any synonym mapping, the function returns this clean, professional version of the label. A list comprehension creates pairs of each raw label and its cleaned version. For every label, the label cleaning function removes extra spaces, standardizes terms, and applies known synonym mappings. Keeping both versions together makes it easy to compare the original text with the cleaned result and trace what changed. The code prints a header showing each original clinical label alongside its cleaned version. This makes the output easy to read and helps verify that the label cleaning process worked correctly. The code compares each original label with its cleaned version and prints both together. This makes the transformation easy to trace, helping show how the cleaning process changed each label. The code prints a concise message showing how many original labels were processed. It highlights that the original labels are kept alongside the cleaned versions so they can be reviewed later. This preserves traceability throughout the cleaning process. This script cleans and standardizes clinical labels while keeping the original text for traceability. It trims extra spaces, removes repeated commas, maps known synonyms to standard terms, and improves capitalization for readability. It then prints each original label beside its cleaned version, making changes easy to review and verify. Basic medical files. Reading medical files. Medical data is often stored in simple line-based files, such as plain text documents or comma-separated tables. To handle these files safely, you must know the file type, location, encoding, and whether each line represents a full record. Opening, reading, and closing files carefully helps protect data integrity and prevents mistakes, such as misreading one clinical field as another. When working with plain text medical files, choose whether to read the document as a whole or process it line by line based on its structure and purpose. Line-by-line processing is useful for large files and record-based data because it saves memory and supports careful checking. Each line should be cleaned, checked for missing information, and interpreted consistently. Incomplete lines or unusual delimiters should be flagged and investigated to protect data quality. CSV-style medical files can be deceptively complex, so read them with tools that understand their structure rather than splitting on every comma. Check for quoted fields, missing values, and the correct separator. Then convert text into proper dates, numbers, and other meaningful forms. Because the data is medical, handle it with precision and confidentiality, even when the dataset is small. Python code. Reading medical files. This example shows how to read small medical files using safe built-in file handling while keeping the output brief and easy to read. We import 3 tools to support common data tasks: pathlib for handling file paths across operating systems, the CSV module for reading and writing structured CSV data, and datetime for working with dates and times. We create a temporary folder for the lesson files using the pathlib path tool. The code then checks that the folder exists and creates it if needed. Allowing existing folders prevents errors and lets the program continue smoothly. The lesson sets up a small clinical text file for practice. It creates a file path in the lesson folder and prepares several lines of discharge instructions, such as drinking fluids and calling the clinic if a fever returns. These lines will later be written to the file so learners can practice reading text files. Open a text file in write mode with UTF-8 encoding so characters are handled correctly. This creates the file or replaces an existing one, then writes several lines from a list into it. The result is a simple text file prepared for later reading practice, while showing safe, efficient file handling. The process creates an empty list to store cleaned lines from a text file. The file is opened in read mode with UTF-8 encoding, using a context manager so it closes automatically. Each line is read, stripped of extra white space and new line characters, then added to the list for later use or analysis. The data setup defines where a vital sign CSV file will be saved, then organizes patient information into rows. The first row contains the column names, including patient ID, visit date, blood pressure readings, and a note. 2 additional rows provide sample patient visit data in the same structure, preparing the information to be written to a CSV file for later processing. To write data to a CSV file, the file is opened for writing with UTF-8 encoding and proper new line handling to keep the format consistent across systems. A CSV writer is then used to write the prepared rows into the file, automatically formatting each row with comma-separated values. The process reads a CSV file into an empty records collection using a dictionary-based CSV reader, so each row is handled with column names as keys. For each row, the visit date is converted from text into a date object to support later date operations. Each cleaned row is then added to the records collection, creating structured data ready for further use. The output provides quick checks that the file data was read and parsed correctly. It reports the number of text lines and CSV records, then shows key values from the first record, including the patient identifier, note, and parsed visit date. It also displays the resolved folder location where the files are stored. This script shows how to use Python's built-in file tools to manage small medical files in an organized folder. It writes discharge instructions to a text file, reads the lines back cleanly, and also creates a CSV file of patient vital signs. The CSV data is read back with dates converted into date objects. Then the script prints a short summary of the lines, records, and first patient details. Writing medical files. When creating medical files, save program data in a durable, well-structured format so it can be used accurately later. Temporary memory is not enough. Files need clear organization, such as consistent fields for measurements and readable text for patient instructions. Use clear field names and avoid vague abbreviations so future users can understand and interpret the data correctly. When creating medical files, choose the format based on the content. Plain text works best for readable narratives such as referral notes or medication instructions, while CSV-style files are for structured records like visits or lab results. In structured files, each row and field must be used consistently, and special characters such as commas or leading zeros should be handled carefully to avoid errors in other systems. When creating medical files, prioritize efficient workflow, privacy, and error prevention. Save each file in the correct place with a clear name that does not expose sensitive information, and avoid overwriting existing files. Always confirm the file can be reopened and understood, since reliable file handling protects important information and supports more complex health data systems. Python code. Writing medical files. Practice creating simple medical files by using safe locations and very small records. After writing the file, check that the saved text matches what you intended. The script begins by importing the tools it needs to work with file paths, CSV data, and dates. It uses pathlib for convenient path handling, the CSV module for reading and writing tabular files, and the datetime module to access the current date in a standard format. The process creates a safe folder for storing medical file examples using the path module, so the folder is made only if needed, and no error occurs if it already exists. It then gets today's date and converts it to a standard ISO format string. This date is used to timestamp the generated files, helping keep them organized by creation day. The process creates a date-based text file name in a chosen folder, so each file is unique and organized. It then prepares patient after-visit instructions, such as staying hydrated, watching for fever, and doing light activity, so they can be written to the file and accessed later. The text file is opened for writing with UTF-8 encoding, so special characters are handled correctly. A header for basic discharge instructions is written first, followed by the instructions combined into one block with each item on its own line. The content sets up structured follow-up call records for storage in a CSV file. It creates a dated file location, then prepares patient records with an ID, record date, and call status such as scheduled or completed. This makes the data easy to manage and write into the file. To write data to a CSV file, first define the column names, such as patient ID, date, and status. Then open the file for writing with UTF-8 encoding and use a dictionary-based CSV writer. After writing the header row, write each data dictionary as a row so the CSV keeps the correct column structure and order. The code checks that the saved files contain the expected data. It reads the text file with UTF-8 encoding and previews the first two lines, then reads the CSV file with UTF-8 encoding into dictionaries and previews the first row. This quick check confirms that both files were written correctly. The code prints a short confirmation that the text and CSV files were created, using their file names for clear feedback. It then shows a small preview of the text file and the first record from the CSV file. This output quickly verifies that the files were written correctly without opening them manually. This Python script shows how to create and verify simple medical-related files. It makes a folder if needed, writes discharge instructions to a text file, and records patient follow-up call statuses in a CSV file using the current date. It then reopens both files, previews their contents, and prints the created file names to confirm the data was written correctly. Updating medical files. Updating medical files must be done carefully to protect data integrity and avoid unnecessary changes. Whether working with text files or spreadsheets such as appointment lists, medication logs, or patient instructions, updates should only add or revise what is needed. Because even simple files may contain sensitive and important information, every change should be deliberate, consistent, and verifiable. When updating files, know whether you are appending new information or changing existing content. Appending adds data to the end and is usually safer, especially for logs and tracking records. Modifying a file requires more care because you must find the correct record, change it, and save the file without damaging its structure. Clear identifiers and careful handling help keep the updated file accurate and usable. When updating medical files, protect the original data by using backups or temporary copies, and verify the results afterward. Careless edits can create duplicate rows, misalign columns, or remove important formatting such as paragraph breaks, which can make patient information misleading or unclear. Always review the updated file to confirm the intended changes are correct and unrelated content was not altered. Python code. Updating medical files. When updating medical files, make changes carefully by keeping backups first and checking the results afterward to confirm the records were written correctly. The code imports 3 tools: pathlib for handling file paths across operating systems, CSV for reading and writing tabular CSV data, and datetime for working with dates. In particular, the date class can provide the current date for tasks like timestamping updates or logs. We set up a folder location for storing data files, then create the folder if it is not already present. Using the make directory method with the exist OK option prevents an error when the folder already exists, so the file operations can continue safely. The process creates file locations for both the vaccination schedule and its backup by combining the data folder with each file name. This keeps the main data file and backup organized, easy to find, and simple to manage. Anonymized appointment data is organized as a list of patient records, where each record is a dictionary linked to a unique study ID. The sample records include arrived and pending appointment statuses, along with brief notes such as OK, call, or reschedule. This structure makes it easy to find, manage, and update individual records by study ID. To create the CSV file, we open it for writing, so any old content is replaced. A dictionary-based CSV writer uses the keys from the first row to set the column headers such as study ID, status, and note. After writing the header, each dictionary is written as a row, producing the initial dataset in CSV format. To protect data integrity, the code reads the existing medical records file and copies its contents into a backup file before making changes. This backup preserves the original data exactly, so it can be restored if an update causes problems. The text writing method provides a simple way to copy the full file content safely. First, the vaccination schedule file is opened in read mode, so its data can be accessed without changing it. A dictionary reader from the CSV module then turns each row into a dictionary, using the column headers as keys. These row dictionaries are collected into a list, making the data easier to work with for later updates. The process checks each current row for the study ID B205. When it finds a match, it marks the status as completed and adds an updated note with today's date in ISO format. This keeps the record current and shows when the change was made. The vaccination schedule file is opened for writing, so any old content is replaced. A CSV dictionary writer writes the column headers, such as study ID, status, and note, then saves all updated rows back to the file. This keeps the file current while preserving its original structure. The process creates an audit log entry for an update. It builds the log file location, prepares a message with today's date, noting that record B205 was updated, and appends that message to the log file. This preserves earlier entries while recording the action for future reference and accountability. To confirm the CSV updates, we reopen the file in read mode and use a dictionary-based CSV reader to load its rows. This makes each row easy to inspect, so we can verify that the changes were applied correctly. The process verifies an update by finding the record for study ID B205, confirming that a backup file exists, and printing the updated record details. It also checks the audit log by counting its entries, helping confirm that the change was recorded properly and the data remains protected. This script shows a safe way to update medical appointment files while preserving traceability. It creates anonymized records, makes a backup, updates one record by its study identifier, and saves the revised file. It also adds an audit log entry and then verifies the results by checking the backup, the updated record, and the number of audit entries. Standard modules. Date handling. Dates are central to medical data because they give clinical context to events such as births, specimen collection, medication use, admissions, and follow-ups. If dates are stored only as plain text, programs may misread them because formats can be ambiguous across locales. Standard date and time tools make these values clear and structured, helping systems accurately compare timelines, such as whether a lab result occurred before a medication change or whether a patient qualifies for screening. In medical data work, dates must be converted from varied text formats into a consistent structured form. A standard date module helps interpret different clinical exports and produce reliable output when data is saved. This consistency supports accurate sorting, sharing, and use across systems, making date conversion an important data quality step. Careful date handling in medical data is essential for accurate clinical timelines and safer workflows. Standard date tools improve reliability by accounting for issues like leap years and time zones when measuring intervals, such as the time between a referral and an appointment. Different records need different levels of precision, from a simple vaccination date to exact timing in an emergency record. Python code, date handling. Structured dates make clinical timelines safer by avoiding ambiguous comparisons. This example shows how medical date text can be parsed into a clearer, more reliable format. The script begins by importing tools for working with dates, file paths, and CSV data. The date and time modules supports parsing and formatting date information. The path class helps manage files and folders, and the CSV module handles reading and writing tabular data. Together, these imports prepare the script for date processing and file operations. We use the pathlib path class to define a folder for storing the CSV file, then create that folder if needed. Setting the create directory method to allow existing folders prevents errors when the folder is already present. This keeps data files organized in a consistent and safe location. The records list stores patient information as dictionaries, with each dictionary representing one patient. Each entry includes a unique patient ID, the patient's date of birth, and the discharge date, both written in year-month-day format. This structure keeps the data organized, compact, and ready for processing or analysis. The process creates a CSV file by setting its path, opening it in write mode, and using a dictionary-based CSV writer. The writer takes its headers from the first record, then writes the header row followed by each record as its own row. This saves the list of patient date records in a clear, structured CSV format. The setup defines March 10, 2026 as the reference date for later time calculations. It also prepares an empty collection to hold each patient's processed information, such as age and days since discharge. This creates the foundation for converting raw date text into usable date values for accurate calculations. The CSV file is read row by row as dictionaries, and the birth and discharge dates are converted from text into date objects so they can be used in calculations. For each patient, the code finds the days since discharge and calculates age by comparing the current date with the date of birth. It then stores the patient ID, age, and days since discharge in a parsed results list. The program prints a summary of the processed patient date information. It goes through each parsed patient record, retrieves the patient ID, calculates the patient's age in years, and finds how many days have passed since discharge. The result is a clear per-patient summary showing the ID, age, and days since discharge. The process converts today's date into the standard ISO string format so it can be reported consistently and clearly. It then prints the formatted date to the console with a report date label, creating output that is easy to understand and use in documentation or reporting. This script shows how to manage dates in medical records by reading patient birth and discharge dates from a small data file and converting them into structured date objects. Using a fixed report date of March 10, 2026, it calculates each patient's age and the number of days since discharge. The output gives a simple clinical timeline for each patient and uses a consistent date format to reduce ambiguity in date comparisons. Safe paths. Handle file paths carefully when working with medical data because files may come from different systems and path formats can vary. Treating paths as plain text can cause errors, especially across operating systems or when paths are entered inconsistently. Standard library path tools make file locations more reliable by building them from clear components, helping programs work predictably across environments. Safe file path handling is essential in medical data management because patient information is sensitive and regulated. Standard path tools help ensure files are stored in the right place, needed folders exist, and files are not confused with directories. This reduces privacy risks, prevents accidental overwrites, and makes data workflows easier to audit and reproduce. Handle file names safely, especially when they come from users or outside systems, because they may contain unsafe characters or try to reach unauthorized locations. In medical settings, using standard library tools to normalize and control paths helps keep programs within approved directories. This protects confidentiality and integrity, making secure file handling both a technical need and a professional responsibility. Python code, safe paths. Use safe paths to protect medical text files. Pathlib helps build file locations reliably without fragile string handling, such as when writing small clinic export files. The code begins by importing three tools: path for safe platform-independent file path handling, date for working with dates, and the CSV module for reading and writing tabular data. Together, these imports prepare the program to manage files, add date information, and process CSV data. Set up a project workspace by creating a base folder from the current working directory, then define separate input and output folders inside it. The input folder stores the original data files, while the output folder stores processed results. This keeps file paths organized and safer by reducing hard-coded paths and related mistakes. The code first makes sure the needed input and output folders exist, creating parent folders if necessary, and avoiding errors when they are already present. It then gets today's date as a standardized text string. This date can be used to label files created on that day so they are easy to identify. The process creates a safe, date-based input file path to avoid naming conflicts. It then prepares a small set of CSV data with a header row and one sample patient record, including a label with extra spaces. This file can then be used for later processing. The data is exported by opening a raw file for writing with UTF-8 encoding and settings that prevent extra blank lines in a CSV. A CSV writer is then created to convert the data into the proper format and write multiple rows, including the header and a sample patient record. The result is a CSV file ready for review or further processing. The code opens a raw CSV file with UTF-8 encoding, so the contents are read correctly, including special characters. It parses the file into rows, then retrieves the label from the second row and second column. Finally, it standardizes that label by trimming spaces, making it lowercase, and replacing spaces with underscores for consistent later processing. To keep file operations secure, the output file name is combined with the chosen output directory and resolved to an absolute path. The output directory is also resolved to an absolute path and treated as the approved location. This makes it possible to check that the final file path stays inside that directory, helping prevent path traversal and ensuring the file is written only where intended. The code verifies that the output file's resolved location stays inside the approved directory. If it does not, it raises an error instead of writing the file. This helps prevent unsafe file writes outside the intended location. The process formats the patient identifier and cleaned label into a single comma-separated message, then saves it securely to a file using UTF-8 encoding. The file is read back with the same encoding, and extra white space is removed to confirm the saved output is clean and ready to use. The process checks that the project and its data files are in the expected state. It prints the project folder name, confirms that both the raw export and cleaned output files exist, and then displays the cleaned record as a brief summary of the processed data. This script shows how to handle files safely in Python using tools for paths and CSV data. It creates a project workspace, writes a raw clinic note record, cleans the record label by normalizing its text, and saves the cleaned result for review. It also checks that the output stays inside the approved folder to prevent unsafe file paths. When run, the console confirms the files were created and displays the cleaned record. Structured output. Structured output gives each piece of data a clear place and meaning, making information easier for both people and systems to use. In medical data, this consistency is especially important because small formatting differences can cause confusion when information is shared. Using standard tools to organize fields like patient identifiers and medication details makes later processing safer, clearer, and more efficient. Delimited text, such as CSV, stores records as rows with fields inside each row. In medical data, commas, special characters, and complex instructions can make this format harder to handle correctly. Standard libraries help keep these files valid, so data can move reliably between spreadsheets, reporting tools, and other systems while preserving its meaning. Structured output helps healthcare teams manage information consistently, making data easier to verify, reuse, and audit. By using standard formats for files and logs, teams can safely track changes, such as updates to patient education titles, without rerunning entire processes. In this way, structured output turns raw text into reliable, portable data that supports accountability and reproducibility. Python code. Structured output. Structured output helps preserve the meaning of medical records, while standard modules provide a safe way to write simple files. Small examples are useful for beginners because they make results easier to inspect and understand. The script begins by importing tools for working with common data and file tasks. It uses modules for CSV files, JSON data, file system paths, and dates, including support for getting the current date. The code sets up an output folder using the pathlib path class, then checks that the folder exists. By creating the directory with the option to ignore existing folders, the program can safely proceed without errors if the folder is already there. A reminders list is used to store structured patient reminder records. Each record is a dictionary containing key details such as the patient ID, the reminder date, medical instructions, and follow-up guidance. This consistent structure makes patient reminders easier to manage and access. This dictionary represents a patient reminder in a clear, consistent format. It identifies the patient, records today's date in a standard format, gives the instruction to check blood pressure each morning, and reminds the patient to bring the log to the next visit. A field names list sets the column order for the CSV file, so each reminder record is written in a consistent structure. It includes the patient identifier, reminder date, instruction, and follow-up fields, matching the data keys and making the output easier to read and process later. The process creates a CSV file for appointment reminders in the output folder, using write mode with UTF-8 encoding and proper new line handling. A dictionary-based CSV writer is set up with fixed field names so the columns stay consistent. It writes the header first, then saves each reminder record as a structured row for clear and reliable data storage. The reminder records are saved as a JSON file in the output folder. The file is opened for writing with UTF-8 encoding, and the reminders list is serialized into it using the JSON module. The output is formatted with indentation so it is easier to read, inspect, and verify later. The code checks a CSV file by opening it with proper new line handling and UTF-8 encoding. It then uses a dictionary-based CSV reader to load each row as a dictionary, making the file's structure and contents easier to inspect, process, or validate. The code finishes by reporting that the structured output example is complete. It shows where the generated CSV and JSON files were saved, confirms how many records were written and checked, and prints the first instruction from the CSV as a quick content verification. This script demonstrates structured data output in Python by creating a folder and saving two medical reminder records as both CSV and JSON files. Each record stores a patient ID, date, instruction, and follow-up action, with the CSV using a consistent field order. The script then reads the CSV back to check its structure and prints a short confirmation showing that the files were created correctly. In this lecture, you learn to manipulate medical text strings to clean labels, notes, and simple patient instructions. Read and write plain text or CSV-style medical data using built-in file handling, and use standard library modules to support safe paths, dates, and simple structured output. In the next module, Module 3, we will go over none.
Thank you for your attention. See you all in the next lecture.